Hello again, and tonight's presentation is Are Black Holes Merely Quark Stars? If you don't know, there will be explaining going on. So some might be familiar with the stellar life cycle of stars. Um, Basically, a lot of gas and dust collect together by static electricity and then gravity, and eventually you get enough of it compressing together to cause fusion to ignite, and you got a star. Depending upon how much of a star you have at the end of its life, which may be many, many thousands of years to billions of years, at the end of its life, it kind of runs out of its primary fusing fuels, being hydrogen, helium, things like that. It starts fusing heavier elements, calcium and silicon and things like that. And when you get to iron, when you go to fuse iron, you're not going to get as much energy out as you put in to doing the fusing. So you kind of run up against a brick wall, which means instead of you producing enough force outward to keep the star intact, you can't, and therefore the star collapses in under the force of gravity, and the outer layers of the star smack up against the core, and you get a bounce back effect, and that's your supernova. But what happens after that? Well, depending upon how big the star was and whether it was a nova, a supernova, or a hypernova, how much of the star is left, you get different things. So if it's small, you get a white dwarf. If it's a little bit bigger and more energetic, you're going to get a neutron star. And the midpoint of, did it collapse to a neutron star, or did it go all the way down and collapse to a black hole? There's this debated observation point called a quark star. So we're going to talk about quark stars, and it has nothing to do with that guy that owns the bar on Deep Space Nine. But first, we have a bit of terminology to get out of the way. In science, they often use the same word that we use in other aspects of non-sciencey stuff. It only gets confusing when they use the same discriminating word, and by discriminating, I just mean this versus that, for two different things. So there are dwarf stars, and there are dwarf planets, like Pluto, but there are also white dwarfs. Now, one puts the word dwarf in the back to say, is it a red or a brown? Meaning, is it it just ignited? Is it a small star? Is it, it's still doing fusion. But stars, a little like our sun, are a little bit bigger, not neutron star size. They collapse down to a white dwarf that's very long-lived, billions of years afterwards. But this is two times in science where the word dwarf just means small. It does not mean a red dwarf, a brown dwarf, and a white dwarf are all the same, point in their life of a star. But don't get them confused. But we're not going to be even talking about white dwarfs. We're going to talk about the next most powerful energetic nova, which is going to be a neutron star. So we're going to take it from, white dwarf. Forget that. That's off on a separate branch. We're going to go to, there are particular types of subatomic particles called leptons. And these are electrons, muons, and tau. And everybody's probably heard of electrons. So I won't get into the family of leptons because there's both the leptons and the anti-leptons. And everybody's probably by now heard of neutrinos. But we're going to do a lot of focusing in on electrons as the things that typically produce, as a result of being energized, they will go out to a different orbit about their parent atom. And when they want to have the atom release the energy, they go back to a lesser orbit. And in the process of doing so, they emit a photon. Neutron stars, in order to convert the protons of the star into neutrons, they do a combination of things where they grab some electrons, take the protons, smash them about, and they convert them. So by the time you have a neutron star and you've taken protons and electrons and smashed them around and made neutrons, but you've still got enough gravity to collapse it even further, what's the next step down? Is it a black hole, or is there a midpoint? Or is there only the midpoint and then a different grade of the midpoint? So the postulation, and you'll see a lot of this, red, italic, bolded. Postulation, that means me being me and connecting dots. Is a black hole nothing more than a quark star? So we'll get into what a quark star is and the different flavors of quark stars. So there are computers.
Wait, go back.
Go
please.
back, okay.
Please.
Okay, yes.
Okay, this chart on the side
Yep.
is new to me, and I know from past experience that you can read a lot of things from it, which I'm not being able to right now. I just look at it and I see that there's purple and green and orange and yellow, and I've heard some of these things. We didn't mention them tonight, like the charm and top and bottom, but I don't know what these numbers refer to, and I don't know why the quarks are above the leptons, if that means anything, or why the orange is on, you know, where they're located. Does it mean anything? What does it mean to you? Can you tell me?
Can I explain?
I was just going to say, you can't read the numbers right now because the original graphic was too low resolution. And I actually went in by hand and I took out just the quark section and I redid it all digitally so that the numbers would be very readable. But that's in a later slide. But yes, Helen, talk to us about subatomic particles.
Okay, it's just in nature, like your body, the stuff that you're eating right now as a snack, everything is made of up and down quarks. So that's the stuff that makes protons and neutrons. So that's the heavy part of any atom that makes your body. And then to equilibrium the positive charge from protons, you have the leptons. The leptons are basic electron, and then when you change positions or you fuse or you have something like that, you have a little part of the electron that would be the neutrino, is another smaller particle that doesn't interact very much, but it's part of atoms. It's part of the inside of, you know, how the atom will work. So only the first line, the U and D and the E and the EV is what it makes your body right now. That's what we interact every time. Everything else to the right is when you have colliders or inside of stars or during the explosions, very energetic explosions in space. Now, the orange stuff is the force carriers. The force carriers, so you have the gluon is the stuff that holds the up and down quarks to make protons. So that will be one of the force carriers. The electromagnetic force is carried by photons. So when you have electricity, you have even the cohesion of your body, or when you touch something that you're not really touching, you have the repulsion of the electrons. Everything that you see there is magnetism, electricity, and electromagnetic. So in that case, light being emitted is carried by the photon. That's the gamma that looks like a Y. And then the Z boson and the W boson, they have to do with how you hold stuff inside of the core of the atom, and also radioactivity. So that's basic. What you have here is the most simple periodic table of nature. So that periodic table that you see there is what makes the other chemical periodic table. That's the physics periodic table, and that the stuff that is represented here it is inside of the atoms that makes the other periodic table that we learn in chemistry. Was that helpful?
Yes, there is one question or one thing that I'm looking at, and I think I know, but like on each one of these little squares, it has the mass, the charge, and the spin.
Mm-hmm.
Okay, so I'm thinking of size of what it is, and then charge, I'm thinking that was what you were talking about with how much somebody would react to if they had a electrical charge. But spin, I'm not. I hear it all the time, spin, and I don't know if we're really spinning it or if
No.
No. But they are comparing the spin to each other. But I don't know what they're comparing if it's not like what I think of spin.
Well, it's just an analogy that we use because when you look at like in chemistry, when you're doing chemistry, you have to understand what is the orbitals of the atoms or how the electron is supposed to be found. So you have positions in areas of the atom that it most probable to find the electron. The same way that you do that, you have the smallest particle that make inside of the nucleus of a proton of a neutron. So it's some kind of analogy that we could use. So inside of nucleons that we call it, could be proton or neutron, you have 6 dimension numbers that you need to find a way to represent. So when they find a way to represent, they use spin and they use colors. There's no colors inside of protons or neutrons, but because you have like 6 varieties of behavior of the probability of the existence of those particles, the way they supposed to be found. And the only way they found it would be if you find 3 things. And then one of the 3 things that we see every day in life is like even the color of your screen that you're looking in right now is RGB. Because if you make a mix of R, G, and B, you end up having white. And then if you remove one or other, you have different colors. So that kind of analogy helps to explain, 6 dimensions inside of a tiny little ball of probability. So it's when you say spin, you imagine a top spinning up or spinning down or spinning to the left or spinning to the right, because you're using, in the case of the electron, you have 2 changes, 2 spins, 2 weights of spin. And why you choose the spin is like it's just 2 kinds of behaviors that the electron can occupy in the atom. So you choose up and down or pointing up and pointing down. So that was an analogy chosen to explain the 2 behaviors of an electron in an orbital. But when you have 6 behaviors that you need to explain and they are complementary, then you give different spins and different numbers that complete one, but each one of them would add to be a third. One is 2/3 and one is one-third. So you can end up having or positive charge in the case of proton or neutral charge in the case of a neutron. So it is kind of weird, but when you understand the numbers, it helps a little bit. But basically, you assign a behavior something that's easy for you to communicate.
But it looks like here that they gave them, well, I don't know, because Monroe did say he went in and cleared it up so we could see it, I guess.
Yep.
I'm thinking. Yeah. But it looks like that the spin is all 1/2 for the top.
No, the
Nope.
one is 1/3.
Yes.
Okay, 1/3. So they're all being 1/3.
So if you add 2 downs and 1 up, you end up having canceling the charges, and you have a neutron object that we call it a neutron. Now, if you have 2 ups and 1 down, you end up adding to be a positive charge, and that you end up having a proton.
Wait a minute, can I interrupt you? Because I've lost you at the moment, and I want to be on the same page. Are you, let's say, if you take the quark and you're saying up, which is U, and you're saying the spin is what now?
Monroe, can you read the spin of U, the up?
2/3. An up is
2/3.
up
Okay.
is 2/3
Okay,
So,
that looks like the charge.
with a
2/3
spin
is
of
the
1/2.
charge.
Yep. Well, have you ever seen an organization that comes up with an acronym and then finds a way to make it fit the words later?
yeah,
we,
that's
we,
basically
we
it.
want to call this DWAG. What does it stand for? I don't know. Go find some words that fit that. Okay. If you want to make an electron, then the resultant charge needs to come out negative. Because
No,
electron.
electron, it is not a mix. It's just one thing. What
Helen,
I'm explaining, the quarks.
Helen,
Uh,
analogy. You
Okay.
want to come up with something negative, the math has to come up with -1. A proton is a positively charged particle. When you get done with the math, it should be a +1. When you want a neutron, well, you got to figure out for it to come up 0. So that's how you arrive at charge. It's not because somebody read on a meter, hey, look, it's 2/3. No, they said, what's the end result? How do we work backwards from that? Well, obviously, that's got to be 2/3 and -1/3. So you mix 2 of these and 1 of those, and therefore you get this.
Does the charge affect the spin?
No, when you say, I want to make a proton, what do I make a proton of? A proton is made up of quarks. A proton is a positively charged item. So if
Is
I
that
take
the one that's in orange? Or are you talking about the proton here or something else?
No, it's
no,
force
proton's
carrier.
not even on this chart.
Okay, all
It's
right.
fermionic matter. You've got
Okay.
inside the atom, you have protons, neutrons, orbiting electrons. That's an atom. Now you want to decompose the proton even further, and you want to decompose the neutron even further. What you'll find is that protons and neutrons are made up of quarks.
Okay.
And gluons stitching things together. But basically, if I want to make a proton out of quarks, I got to combine a certain number of quarks to come up with an end result that has a positive charge, because it's a proton. It has to. So what am I going to do? Well, if I ram 2 protons together and I see multiple things flying out, and I see 2 like this and 1 like that, then for the math to work out, it's got to be 2/3 and -1/3 to come up with let's add them together and oh look, it's positive. So if you look at the charge and if you look at the spin, it's creative math. Like, is it precisely 2/3, or could it be like a fractional number? 2/3 is 0.66666. Could it be like 0.5? Well, not if it's charged, because charges have to add up. But look at the number directly above it, the mass. Why is there an approximation symbol next to mass? Because mass relates to energy, and in our observations, we found that, well, this particular kind of quark, an up quark, is in the ballpark of 2.3 million electron volts per speed of light squared. That's the flux, like how much mass is an up quark conveying. It's not a precise number. It's not an arbitrarily selected thing like charge and spin. It's a measured value. So you pigeonhole it and you go, well, everything that's in this approximate range is an up. Everything that's in this approximate range is a down. It's not.
And you're talking about
up
spin.
and down.
You're talking up and down spin.
Right, but it's not really up and down. It's this range of energies, this mass, versus this range of energies and this mass. But they got to give them a name. What do they call them? Up and down, because we've got top and bottom. And then when they found out more, and they went, what do we call these? Charmed. Oh, we found another one. That's strange. Oh, strange. So a lot of this is what the general public doesn't get when you first start looking at this. Is that one charmed? What is the charm that it's got? Like, no, it's just a word. It can be called hippopotamus, but it's just a word that they assign to the values of properties for collections of things.
Of quarks.
Yeah,
In this particular section.
quarks.
But are the quarks and the electrons related there? And that's
Yes, they're all subatomic particles that are, to our current knowledge, indivisible. You can't smash them and break them apart any further. They're indivisible subatomic particles. But quarks have a different conveyance characteristic than leptons. So if you look at quarks, you look at the mass of them. You look at leptons, you look at the mass of them. An electron carries energy. It carries energy by way of photons. But quarks carry matter. They carry mass. So they have different functions, and that's why you see them in different colors here, is just to break them apart and say, well, all the quarks do this, and all the leptons do that, and all the gauge bosons do this, and we think there's another thing out there. We're going to call it Higgs, and it's a scalar boson. It's a boson, but it's a different kind of boson. So all they're doing is, hey, we broke something apart with a little more energy, and we found some new particles coming out. What do we call them? Are they different or similar to the stuff we already have? Well, if they're similar, we just add another one to that coloring. If they're different, we add a whole new coloring, like Higgs. So what happens if they discover that, oh, we found a new category of quarks that are nowhere near as massive as top, but far more massive than bottom? Because when we get to the details, you'll see some of these numbers vary quite widely, and if all of a sudden we find a new particle that fits in the middle, it's all broken. It's not that it won't work, it's just our artistic rendering of the table and how we have everything pigeonholed by charge and spin, and this has got that, and that's got this, and that's how the math works out. All of that, like, you need to go back and look at that again because it's not working. And a lot of times it would just be, well, widen the bucket and just put it in with the other stuff. So some of the physics that they play is gamed physics. And if you don't know the game, you won't see that some of these guys are just grabbing at straws.
So now we've seen the game.
Yeah, now you've seen the game. Colors aren't colors, spins aren't spins, and they're just putting labels on stuff that they find that are different. And you've got values of a property that are different, and then you've got different properties. So anyway.
Thanks both of you. Thank you both.
Yeah, we have computer simulation models for the behavior of a white dwarf, the behavior of a neutron star, the theoretical behavior of a quark star, and what goes on inside of a black hole. So I had to put the picture of the black hole. But that's not a picture of the black hole. That's a picture of the matter on the outside of the black hole falling into it that is energized and therefore producing photons. And this picture is actually in radio, not visual light. So they've mapped the colors onto pretty colors that we can identify with. But the darker red stuff is, lower frequency radio waves. The brighter stuff is higher amplitude, shorter frequency radio waves. But this is our picture of a black hole. So the fact that we don't have a picture of a quark star doesn't really mean anything because we don't really have a picture of a black hole itself. We have a picture of the observational interactions of the black hole. So it has been postulated that quark stars might be similar to neutron stars because they have a lot of the same characteristics, but not quite like black holes. They may be like a midpoint. So if you have a star that goes nova and starts collapsing down, and it doesn't become a white dwarf, it collapses down even further. It smashes the protons around with electrons and makes just neutrons, and it gets denser, and now you have a neutron star. What if it was just a touch bigger when it started collapsing down? Is a black hole the next step beyond a neutron star, or is there a midpoint, a quark star? Well, turns out that if you look at the gravitational energy levels along a curve of where a neutron star is and where a black hole is, there's plenty of room in there for something in the middle. So a lot of the astrophysicists say, well, it's a quark star, because they know in subatomic matter that after you degenerate protons into neutrons, that you can take it to the next level and degenerate the neutrons into quarks. So quark stars. So I look at it as, why are we ignoring what's right in front of us? In other words, we know that when a star collapses, it can become a white dwarf, and if it's bigger and the gravity is stronger, it could be a neutron star. And when you look at how that process occurs, you can see that it's a trending mechanism. And if a quark star is the next point beyond a neutron star, is there a point that's still a quark star that's beyond where a quark star would be on that path? And it turns out there is, yeah, a quark star, but a quark star with different kinds of quarks in it. So I'm just saying, I think that you go from a neutron star to a quark star, and if you go to a really quarky quark star with far more energy, far more mass, far more gravity, you don't wind up with a black hole, because a black hole mathematically has too many boundary conditions that mathematicians don't feel comfortable with, like singularities and a black hole itself, and it all goes in and nothing comes out. Even Hawking said, you're right, nothing comes out. And then later on he said, I don't see how we can obey certain laws that we've already stated as like conservation of matter, of energy, of momentum, and still have a black hole. So we're going to let a little bit out every so often, and we're going to call it Hawking radiation, named after Stephen Hawking. So if it becomes proven, and it's nowhere near proven yet, that quark stars taken to the extreme are uniform types of quarks, they're singular types of quarks, and that's the limit, then maybe all black holes are nothing more than quark stars of a single kind of quark. So here's the properties. The parallels between a quark star and a black hole are gravity greater than neutron stars. Check. No direct observation possible, because no light, no radio comes out of a non-feeding, fully formed black hole. Quark star, check. So one of these things does seem like the other. So let's take it to the next level. Let's postulate one of these things is the other. For all of the print material we have and all the research that we've done, maybe black holes are nothing more than the next step in the degeneration process from neutron stars to quark stars of a singular type of quark. And we can see this as protons degenerating into neutrons, you get a neutron star. Neutrons degenerating into quarks, you get a quark star. Various kinds of quarks finally degenerating to a singular type of quark, you get not a heterogeneous, but a homogeneous quark star, it's kind of like fusing iron. You can take these degenerated progressions down to a certain level, and you hit a point where we got nowhere else to go. Like fusing iron gives you a supernova. Well, maybe when you get to the next level down in degeneration of quarks, you get to a stopping point, and that's kind of like what we're calling a black hole. So all of the exotic stuff that we're predicting, like black holes have hair and fur, and like, because we can't observe inside of them, we're making guesses, postulations. We have no technology to make those observations. We're just saying, what if? Maybe we don't need all of those if we just go, well, maybe it's just a singular type of quark, and we're really at the bottom, that same bouncing our head against the bottom, and we don't need anything as exotic as singularities and infinite gravity. It's just like, it's a singular type of quark. But once we get there, and if you watch the PBS video later on as your homework exercise, you'll find that normally when you break apart things, some quarks don't last very long. Other quarks last a little longer. And what they've latched onto is they picked a kind of quark that lasts a little longer, as that's where we're going to degenerate down to and stop there. Well, there's another higher mass kind of quark that they kind of ignored as that's much higher mass. Why aren't you stopping there? Because the only observational evidence we have is we're stopping here because it lasted a little longer. Okay, so this is a little bit bigger, but this still has the other particles in it. So I'm going to skip ahead. But the one thing I will point out here is we've thought for a long time in science circles that these are indivisible subatomic particles. You can smash together protons all day long, and you're not going to get quarks to break apart into new kinds of things. But as we make colliders that have even greater energy, we start doing things like smashing electrons together. We're going higher energy than trying to smash protons together. We flip the charge, and instead of positive for proton, we're going negative for electron. We just flip the direction of the magnets, and now we collide two electrons together. What happens when you collide two electrons together? Well, you get electrons. But the energy has to go somewhere, because if you start with two electrons and you smash them together and they scatter, there's got to be, where you put the magnetic field into the electrons and accelerate them. When you smash them together, that abundant head-on collision energy's got to go somewhere. So it produces scattering of electrons and photons. And it's very normal when you energize an electron for it to go, I've got too much, let me get rid of it, and a photon. Well, they've smashed photons together, and it's not 6 sigma yet, but there are multiple observations of smashing photons into other photons. Now, how do you do that if photons don't have a charge? Well, photons don't have mass too, but they do have momentum. And if you can take two particles that are highly energized and you smash them together, when they want to produce photons, the alignment may be such that when you smash those two particles together, the photons that want to come out in opposing directions, and now you have a photon-photon collision. And when you have a photon-photon collision, which is rare, you get muons and anti-muons. And if you look down below the quarks, you'll see the green stuff, and those are leptons. And leptons are electrons, muons, and tau. Does that mean if I smash two photons together, I get out muons and anti-muons? I thought photons were indivisible. It's not 6 sigma yet, so just ignore the man behind the curtain. But do keep an eye on the effort to get photon-photon collision observations, because they've got at least 2 observations by different groups that say it produces muons and anti-muons, which, think about it for a moment, muons and anti-muons, if they are near each other, they produce just energy because antimatter and matter particles, yeah. So protons and neutrons are called baryonic matter, and they are composed of quarks held together by gluons. So just think of it as the purple guys at the top, we're going to be focusing on those. All the rest of the stuff is like crumbs. They're like the leftovers. And here's that table a little bigger. So most of the electrons in the star were lost during the proton conversion. You take electrons and protons, you smash them together. Now we got neutrons. What happened to the electron? Well, you get photons out of it. Well, what happened to the electron? You got no more electron. Or you've got a great reduction in electrons. Okay? Without electrons, how do you carry away magnetic fields? Well, in neutron stars, there are obviously some electrons left because neutron stars have intense magnetic fields. And in fact, one kind of a neutron star has magnetic fields so intense, it has its own classification. It's called a magnetar. It's a magnetic star. It's a neutron star with such intense magnetic fields, we gave it its own classification. So if you have very few to no electrons because you lost most of them when you became a neutron star, where are the photons coming from? Well, as you become a black hole from a neutron star, there's a lot of stuff around you. There's a lot of debris. There's a lot of stellar matter that's collapsing in to create the black hole or the quark star. And therefore, you still have a lot of material, a lot of leptons that can carry away charges and can produce photons. So maybe it's not intense gravity that won't let the photons escape. Maybe it's simply there's not enough messenger particles, not enough electrons to carry away the energy as photons, and therefore we need to look at other types of messengers for carrying away the energy. And if you look down here, you'll see that it's kind of a bit fuzzy. I don't know if you can make out the numbers. Do you see the 2.2 in the up quark? Okay, in the up quark in the top left corner of it, you see the 2.2? Forget about the units of measure, but 2.2. Do you see that?
Yes.
Okay, so you see when you go over to charmed, it goes 1.28, which is a smaller number, but do you see the G? That's billions, giga. And down the lower left, you see 4.7 M, and then strange, you see 96 M. And then when you go over to the right, you see bottom at 4.18 G and top at 173.1 G. So if you were to look at all 6 of the possible quark types, and you were on the path towards degenerating particles to the maximum mass density because gravity is just crushing things in, if you take your ups and your downs and you crush those together, you're going to take 2 ups and a down and make it into 1 up and 2 downs, which means you're going from 2.2s more towards 4.7s. So you can see you're making the mass bigger and you're reducing the total number of quarks. That's a progressive process.
No, that's not how it happens. They continue the same number of particles. The thing is that they are crushed together and they get more concentrated in a smaller area.
So you're saying that 2 ups and 1 down do not become 1 up and 2 down.
No, what I mean is that when you quash the all up and down together, two downs and one up together, when they quash together as they become a quark star, they're gonna be just pushed together to a point where they destroy the cohesion of the neutron and goes just like closer together.
It already did that when it became a neutron star. I'm talking about the next step when they become a
Yeah,
quark.
the quark star. You
No,
destroy
no,
the
no,
cohesion
no.
of the neutrons and push them close together.
I agree that
They
they're
don't
getting. I agree
transform,
that
they just
I
lose
agree that
cohesion.
I agree that they're getting pushed closer together. Where we differ is on the progression. How did you get a neutron star to begin with? You took protons, which were made of what kinds of quarks?
Two ups and one down.
And you made a neutron out of it, which is what kind of quarks?
Now two downs, one up.
And what's that progression?
I don't understand the question.
Okay. What was the process where you started from and where you ended after you took a proton and converted it into a neutron? You went from two up,
You
one down.
end up with a more massive particle.
Exactly. So you
But
went
because
from,
you added the electrons, they were in the outer layers of the stars.
right. So you went from two up and one down to one up and two down.
Yeah. But
Okay.
you remember that before, when it was like, the mass of a white dwarf,
Mm-hmm.
before you had the addition, the crushing down the stuff,
Mm-hmm.
you have full atoms. Uh, uh, they were ionized, and then those electrons just get, pushed down together, and you end up forming only neutrons. So you don't have a full atom anymore that gives a farther part. They have like the electron degenerated pressure, and the atoms don't like to be close together. That's what sustains the star, and what gets pushed together to be the white dwarf concentrated. But when you push further, you don't have an atom anymore, so now you have a way much smaller particles. They're close together, so now you have like a giant billiard. You have giants like let's say basketballs in a in a in a basket, and then you crush together. Now you have billiard balls, so they're closer together. Even though they have almost the same mass, they're closer together because now they're smaller pieces of what was before, and they're in those smaller pieces they can concentrate it closer together and have a more dense object. You didn't change the mass at all. So like, if you imagine the analogy that if I snap my fingers and the sun became a black hole, nothing would happen with the orbit of the Earth because the sun kept the same mass. As the only thing that was different that before was a ginormous star, now it is as small as the planet Earth. And then in that case, it has a massive body, but it's concentrated at mass.
But the progression was towards greater mass in smaller space.
Yeah.
Okay.
So
So that's how
larger
you
densities.
that's how you get a neutron star. When you want a quark star, the same thing happens.
Yeah.
You're on a progression, 2 points on a curve heading towards maximization.
There is no more mass, it's only more density.
Correct. So if I add 2.2 times 2 plus 4.7, I get a proton. Right?
Mm.
Okay. If I add 2 times 4.7 plus 1 times 2.2, I get a neutron, which has greater mass. Right?
Yes, neutrons more massive than protons.
What's the next most massive after a neutron that is a quark composite?
Only if you have an equivalent of like, I forgot the name. Kaons. Kaons are made of the top and bottom, I think,
Yep.
quarks.
Now, why would it be that and not charmed or strange?
I just can't recall particles made of charm and
Because
strange.
the mass is that much bigger in the same space. You go from millions of electron volts to billions of electron volts. And that continues the progression. So if I'm going to go from a neutron star to a quark star to a quark star with a singular kind of quark, why would I go to strange when it's like not all the way there yet? It's a midpoint.
They wouldn't be a singular kind of quark. What they postulated is that half of the down quarks would become some other more dense kind of quark.
That's where they come up with strange.
Yeah,
And why did they choose strange?
because it's a smaller smaller volume. It becomes more dense than when they aggregate together.
Oh, I agree that you're going to have greater mass, greater energy in a single particle space, but why strange? Why not top?
It's like if I choose to occupy a small space, the most that I can, if I use ping pongs to put in a cylinder, I would have less dense if I fill the same cylinder with sand.
Exactly. So
I would choose strange because strange is tiny.
but top is even smaller.
No, top is just ginormous.
Okay, then why wouldn't I make everything out of up or charm? Actually,
They
the
cannot be just one kind of. You have to follow. You won't like what I'm gonna just say. You have to follow the chromodynamics.
Uh-huh.
In the chromodynamics, you have to have different kinds of quarks together,
Okay,
and
why do
so
they call
you're
it
gonna have up and down
why do they
and
call it a strange star?
strange.
Why do they call it a strange star?
Because it's half of the down quarks became strange quarks,
Uh-huh.
and I think you could make maybe is triple. I forgot the name of the thing. It is you can pick tet tetraquarks, pentaquarks. You know there's, but I don't think they can survive in a quark star. It's just loose collections of just like a lattice, a crystal lattice of up and down and strange quarks.
So let's get back to the progression. And
Sure. Sorry.
if a black hole is supposed to be the ultimate progression of stellar collapse, why do we stop on quarks? Why not a progression that takes it to the limit? I don't want two particles to occupy the same space, but as you've indicated, if I have a small enough particle, I can pack them denser in the same space. Now, if I created a strange star out of strange matter, what would be the gluons that would hold it together? Would they still?
It won't be a gluon because it ceased to be a
Oh,
baryon. It's not a
no,
baryon anymore.
right.
Now it is in a state that is in a quark soup or quark crystal lattice,
It's no longer
depending what you read.
it's no longer a quark gluon plasma. It is just quarks.
Yeah, it's like a soup. It doesn't make a full like if it would be a baryon, and would be a gluon and three quarks, or it wouldn't be. It's just a soup. Yeah, you could say a soup of plasma,
Right.
quark plasma.
Right. If you look at the research material towards the end on strange stars, the reason why they picked strange is because of the observational evidence from collisions that top didn't last as long as strange. So if you wanted a stable quark star, it would need to be strange quarks, because that's the stable.
Yeah, that's
Except
what the
if you,
hypothesis says.
yeah, except if you look at the research paper on quark stars, it actually says it might be strange if the only thing you followed was the observational evidence of a non-6 sigma observation that says strange lasts longer than top. But once the gluons are not a factor anymore, there's no problem with having a single type of quark and it packing as dense as you can get it.
I don't think they all would transform.
Over how
I
many
don't know.
billions of years?
But quarks are fermions, so they obey Pauli exclusion, so they can't pack infinitely, I think.
You're correct, and I never said infinite packing. I actually said...
I understood that? Oh my God.
No, I actually said, I believe the Pauli exclusion principle does work for quarks. You can't have two quarks in the same space at the same time, but you can have the most possible number of quarks in the smallest possible space, and a neutron star is not that. And a quark star that is strange matter is not that. A quark star that is all top is that. Okay, next slide. So what other stuff might come out of a quark star even before it's a singular type of quarks? Maybe neutrinos, but remember where neutrinos come from. Fusion. So once your nova occurred and things stabilized down, what fusion remains? Well, you're already below atomic level. You're below subatomic level. You're down into individual indivisible particles. So there's not really any fusion taking place. You've gone below, you've increased energies and gone below the level of fusion. So neutrinos might start coming out when you first get your quark star as like leftovers, but eventually when there's no more fusion going on, even neutrinos should stop coming out. But you still have energy that you have to get out of this thing that you're continuing process on. Gravity, we know, is not a deterrent to neutrinos, so no matter how densely packed the neutron star is or the quark star, if there's still a fusion reaction going on, you should see neutrinos coming out of it. And we can measure certain kinds of neutrinos these days, but not all of them, just like gravity waves. So, but as we find out more about neutrinos, we find that neutrinos from fission reactors are easy to create. Neutrinos from stars that are nearby, those we can see, but as we look out into the open space, the neutrinos get to be very, very energetic and very, very infrequent. So they're on their own progression. Now, you might still get neutrinos out when you have a black hole or a quark star that is feeding. So as stuff's coming in and it's degenerating into quarks, you can get neutrinos out, because neutrinos are always thought of as like the leftover breadcrumbs. When you do the math and you come up with like some leftover, that's the neutrinos. If you have too much coming in that you can't even make neutrinos, you just have electrons and magnetic fields, and that's where you get your polar jets and your quasars, your radio waves coming out of the stars. But once the feed rate, once the amount coming in is less than or equal to the rate at which particles are degenerating, becoming like quarks or singular types of quarks, you come to a process rate where it's not a matter of a distance, it's a matter of if I have no more stuff going in and I have no more excess stuff spewing out, I can now have a quark star go silent because it has no means of producing photons that will be something we can see, because it no longer has the messenger particles necessary to produce a lot of that we can see, across the galaxy, across the universe. So you can think of the event horizon of a black hole is not so much a distance as it is when matter falls in and gets degenerated, it produces debris. That debris can be polar jets, that debris can be neutrinos, that debris for a while on the outer perimeter can be photons. But once you've fed all you can feed in, or once the amount coming in is not sufficient to overpower the degeneration process, you're going to have fewer and fewer photons coming out. So it's a process rate, a threshold that you've achieved, and you're now under that, so you're not going to get that stuff out. You still have energy you need to spew out, but you're just not going to have the messenger particles to do it. Here's the blown up chart. So a neutron star is a degeneration from ionized atoms down to neutrons. Basically, we take protons and electrons and smush them up and make neutrons out of them. So a quark star would be compressed down by gravity to the next step. It'd be comprised of quarks, no longer neutrons. And you can see when I take my protons, which is 2 up and 1 down, and I smush it together, it becomes 1 up and 2 down. Now, up is 2.2 million electron volts, down is 4.7 million electron volts. So you can see that the process is moving from lower to higher energy. And you're going from 2 up and 1 down to 1 up and 2 down. So you're decreasing the quantity of lower mass, lower energy quarks towards the higher mass quarks. So it's a progression, just like you go from, protons to neutrons, and then from neutrons to quarks. What's the next step after that? And what they're saying is, well, it's going to be predominantly strange quarks. So the quarks are going to change their flavor, and we know that when you change the flavor, you're going to change the mass, and you're going to move towards greater mass. So you're going to take some of your quarks and convert them into strange quarks. And if you look at up and down versus strange, you see the number at the top, 96 million electron volts. So you're once again taking small energy and making it larger energy, and taking multiple kinds of quantities, and you're going from larger quantity of smaller to larger quantity of larger. So the statement that we're going to go from 1 up, 2 down to 50% of the ups and downs are going to be converted to strange. Maybe that's all the leftover energy it has at that point, and that's why you get some strange out of it. But is that the final step? Is that, on the process curve, is that the final step? It's not. It's the one in the upper right-hand corner. So instead of going to strange, why wouldn't they go to top? And if they're moving along that path, why wouldn't they go to eventually all top? And people will say, well, the ups and the downs are together held by gluons. Well, once you go to the next level down of packing density, where if you watch the PBS video, talk about, they're held together basically by static. Well, what if they're the same charge? Well, a lot of the proximal forces that we talk about, like strong force and weak force and things like that, you start to get below the levels of that effect, and you can now have a stable, strange star. Well, per our particle collision observations, strange quarks shouldn't last all that long. We know that ups and downs do when paired and tied together with gluons, because you've got protons and neutrons. But once you break them apart and the gluons are not a factor anymore, how dense can you go in the absence of gluons? And strange is like on the way there, but not quite there. In fact, you could say, well, maybe it's not strange, maybe it's bottom, because bottom is at least in the, more than 1 billion electron volts per speed of light squared. So
gluons carry the strong force, right?
Yep.
Our top quarks have a charge?
2/3. Just like
not a spin, a charge. Oh, I'm sorry, it is a charge of 2/3.
Yep.
And yeah, it is like it is strange when our mind, because we learned like regular electricity, you have positive charge and negative charge. But when you go to quantum, the charges get more complicated. How you explain that you have 3 charges? That is kind of weird. So they found a way to find analogy.
That's nothing. The spin of one means you rotate it 360 degrees to get to the front again. A spin of 1/2 means you have to rotate it 720 degrees, right? Yeah,
Yep.
I know quantum is crazy, but the question is, my understanding is that the strong force overcomes the electromagnetic force at a certain size, that the reason protons can be held together within a nucleus is because the strong force mediated by gluons overcomes the electromagnetic force of repulsion. So if you're saying there are no more gluons and yet there's a charge, what do you have, a fifth force that's holding it together?
And that's why
gravity is pushing everything down. That's forcing everything down.
That's
why gravity is. I'm sorry. So gravity, of course, in general this week. Are you saying that it is so close that gravity is stronger than the electromagnetic force at that scale?
And the strong force.
If you look at the PBS video on strange stars, you'll see that once you get 50% of your ups and downs to become strange, you don't need the gluons anymore to hold it all together. Because
I don't know that one on spin already broke my head. I think I'm going to stack overflow.
Your local pharmacy
overflow.
Your local pharmacy has all sorts of anesthetics for brain hemorrhage.
and listen, I've been reading this for 10 years, and it's like the first years that I read my physics books to do the course for NASA, I read and memorized to pass the test, but what I read, as I explained and taught many times, is when my mind kind of figure out a way to see in a different way. It is very hard for you to convince your brain that quantum, it is so weird and it's normal, because it's not normal.
It is very normal because they fudge the math in order to make it work. If you look at mass is a fractional number. It's a floating point number. It's got many digits on it. This is just like showing a couple of significant ones. They actually go out about 6 decimal places. But what they do is they range them. They say, we're going to call an up anything that fits within this range of millions of electron volts. So it's about 2.2, where 2.2 is like, full width, half max value. And they do that with all the quarks. But when it came time to say, well, how do we describe the interaction between this quark and this quark? Give them charge and give them spin, because you'll see that the numbers work out. Well, why is it 2/3? Why don't you just say 0.666? Well, why is it not 0.5? Because that would be a half, and a half doesn't work out. So when you start adding together, let's see, I've got 2 up. That would be 2 times 2/3. 2 times 2/3 is 1 1/3. And I've got 1 down. Well, if I've got 1 down, I've got a negative 1/3. So if I've got 1 1/3 and I add a negative third, what do I get? 1. What next bigger particle after quarks has a charge of 1 plus 1? Oh, goodness, that'd be a proton. That's how the math works, folks. They fudged the numbers to make the end result be what they believed it to be, 1920s. So
it works still today.
And it works because the math works for what the math works for. Now, is it numerically precise? Hell no. The only thing that's numerically precise is the mass, not the charge and not the spin, but the mass is not a unique value. It's a range. So if all of a sudden you said, well, if I look at up, it's 2.2 million, and if I look at top, it's 173.1 billion. That's a very wide range. But let's sneak in another one. We've got another one that it's not quite a top, but it's far more than an up. What are we going to call that one? A bottom. It's clocking in at 4.18.
Hey, if you get to discover, you get to name whatever you want.
But you're never going to discover another one. You know why? Because the picture works. We got a nice 6. 6 fits so nicely in our box. If somebody came up and said, I've got a 7th type of quark, you would be shunned in the physics community because you break their pretty picture. Well, what would its charge be? It's got a negative 1/5 charge. No, that can't be possible. Why not? Because it would break the math. Well, if it's an observation and you've got multiple colliders that can repeat the observation, and you do that and you come up with 6 sigma, I don't care about your damn silly graphics or your funky math. It's a new kind of quark. And until somebody comes up with a more energetic particle collider to make that happen, we very comfortably and can sleep safe at night knowing we've got what we've got.
For now.
Until somebody comes along and proves us otherwise. But as that clever guy Carl Sagan once said, what did he say, Helen?
I don't know.
He said a lot of things.
No. What requires extraordinary evidence? Extraordinary observations.
Yeah. Extraordinary claims require extraordinary
Evidence.
evidence.
Yes, but if I have an energetic enough collider and it comes up with a 7th kind of quark, and it's somewhere between 4.18 and 173 billion, there's plenty of space in there for another one to exist. And if it did, and you had 6 different observations that all came away with the same ballpark number, and it created a new grouping between bottom and top, how much pressure do you think the community of particle physics would exert to make it not so? Because it would break our picture and our math, and it works so well now.
Would it make a difference?
No, because most of the mass is made of the 2 kinds.
And that's why they are getting away with mass that is bounded by type. So if you look it up, you'll find that up is the lowest mass, lowest energy quark. It's 2.2 million. We found one that's a little more than double that. But how many are we finding that's between the two? Well, there's lots of observational evidence that's between the two. They just picked an arbitrary point that's an average between the two and said, you guys go over here, you guys go over there. Why do you think there's that little approximation symbol? Because they actually have observational evidence that says we've got observational evidence for values that are between these. But there's not enough of them to warrant breaking up the pretty picture or hurting the math. But once there is, you're going to see an enormous amount of back pressure no matter how many times it can be demonstrated that no, it can't happen. Because at one time, there were 103 elements on the periodic table, but people said, I think there's room for more down here in this area because the numbers allowed for it. And in quarks, there's plenty of room. The numbers allow for it. So to make sure that you didn't have more of them, they put boundaries around the numbers, which is why you have your little average there. And as long as they fall within that average, it's an up, it's a down, it's a charm, it's a strange, it's a top, it's a bottom. But if you have a particle collider that suddenly comes up with something that's between 4.18 billion and 173 billion, it just falls between the two. Trust me, no matter how many observations they come up with, the momentum will be, it's an up. No, sorry, it's a top or it's a bottom. We're not coming up with a new kind of quark, no matter how many times you find one, because it would hurt the pretty picture. Anyway, so.
It doesn't serve a purpose, really, because, I mean, what are these quarks? Would it serve any purpose having a number 7?
Oh, it absolutely does. It's called new science.
Okay.
We didn't start out with just up and down for long. We started coming out with up, down. Oh, we found some more. Oh my God, those are really energetic. Top and bottom, because up and down, top and bottom. There you go. Wait a minute. We found one that's between those. It's charm. We found another one that's a little more, but still between those. Strange how that is. Okay, there you go. So when they found new stuff, as long as it fit, they allowed new types of quarks in and they spread the picture. But now that it's all nice and stable, and I don't mean stable from a quark perspective, I mean stable mathematically and visually. If suddenly you created a particle accelerator that came up with a new kind of quark that was readily reproducible at the midpoint between top and bottom, they're just going to arbitrarily scoot it over to make it a top or scoot it over to make it a bottom. Because what happens if they come up with an even higher resolution particle accelerator and they find, hey, there's midpoints between all of these. So instead of 6 quarks, we're talking about 12 kinds of quarks. Oh, that would really put a hurting on the picture. So there is containment in order to create emotional stability for the people that draw the picture and the people that do the math that come out with the number before they come out with the numbers that make up the number. And if you don't think that was true with protons, how about neutrons? What's the charge of a neutron? 0, got no charge. How did it come up with that? Well, let's see. If we have 2 downs and 1 up, that would be 2 negative 1/3 and 1 positive 2/3. Oh, look, it's a 0. Well, that's the way
That's how
particle
it
physics works. Is we've got a proton that's a +1 charge. We've got a neutron that's a 0 charge. How do we get quarks to fit the math? Well, we'll give them a charge of 2/3 and -1/3, and there you go. So it's almost like we've got the observational data. Let's come up with numbers that make the end result fit the goal. You think they ever found a charge of an up that was less than 2/3 but more than 1/3?
Quanta.
Of course.
It
Of
always
course.
specific levels until it gets to the point. There is no in between.
Yep. Right up until we come up with a particle accelerator that can take us to in between. Remember, at one time, we didn't have a particle accelerator that could break protons apart and come up with quarks. As the technology improves, as the accelerators improve, we find new particles, and we always put a stake in the ground and go, I can't dissolve this to anything smaller. It's indivisible up until it isn't. We're not going to find any more of these up until we do. So it's a comfortable plateau. So getting back to it, if I have a neutron star and it degenerates down into a quark star, I get that initially it will take its neutrons and convert it to, a lower number of quarks with a higher mass. That makes sense to me. But then when they say, and there's another step we can go through where we take those quarks and we create an even greater mass. Do you stop there? Is there another point where you're going to get an even greater mass? And they've stopped at strange because strange is comfortable and it's a cutesy name. But I don't think it should stop there. I think the progression should continue until you have a conversation with the late, great Pauli, or you have a conversation with some guy named Planck. And then you can stop. We're not there yet. Now, once you said, I've still got energy that wants to come out, if I haven't got any of my regular messenger particles like electrons to create photons to get rid of that excess energy, how do I get rid of the excess energy when I'm converting multiple kinds of quarks into a single kind of quark? I've got excesses. What do I do with my breadcrumbs? The way you get rid of your breadcrumbs is through gravity waves, gravitational energy, gravitational waves. But what kind? Well, we already know that if you take two neutron stars and you rotate them really close together until they smash into one another, you get a gravity wave. And we've measured those and we've confirmed the existence of gravity waves. And we have at least 3 gravity wave observatories on the Earth that have seen multiple gravity waves due to neutron star collisions. But what they've seen is high amplitude, low frequency gravity waves. So it's like having a radio dial and all you can hear is the really loud AM radio stations. And that's all you can hear. So do the other radio stations not exist? No, of course they do. FM exists. You just need to go get yourself an FM radio tuner. Same thing here. We're now finding out that theoretically gravity waves should exist at different amplitudes and different frequencies. So how come we can't pick them up? Well, if you've ever looked at LIGO and Virgo, you see these really long gravity wave tunnels, and they're counting on the gravity wave to ripple through at an L shape at 90 degrees to one another and change the distance between the laser source and the mirror that's bouncing it back. And therefore you can detect the difference between one side of the L and the other side of the L by, half the diameter of a proton. Billions of times smaller than a human hair. And you can do that, and you do that reliably. But what if the amplitude is smaller? You won't even see it because it's below the threshold of your electron detector that produces your analog to digital conversion, so you get a number out. It's below your signal to noise ratio. So what would you get out when the amplitude is below your threshold? A zero. Just because it's a zero, does that mean it doesn't exist? No, you need a better detector. Okay, same thing on frequency. If you're looking at low frequency, if you said, I've got really good cameras that can see in infrared, long wave, very long waves, low energy, long waves. Could I see ultraviolet with that? No, of course not. Does that mean ultraviolet doesn't exist? No, it just means you don't have the technology for observing that something exists. So what do you have to do? Oh, go off and create the technology. Well, there are people that are attempting to create gravity wave detectors that are very much smaller. They're like tabletop size gravity wave detectors, but they have many, many times higher thresholds of amplitude on their detection mechanisms. When you want to detect gravity waves, you have a very small amplitude, you have amplifiers. And as we make amplifiers that are better and lower noise, we can take smaller and smaller quantities of billionths of an ampere down to, femtoamperes, and we can amplify that up, and now we can get a digital value out of it. So we have a solution for the amplitude not being high enough. We just make more stages in our amplification, and we have, instead of having 8-bit detectors, we make 12-bit detectors. So we can now start to see what we could not see before. That's for amplitude. What about for frequency? Now, frequency is a little tougher because there's this guy named Nyquist that said, if you want to sample a frequency of X, if you want to detect a frequency of X, you actually need to sample at a frequency of 2X. So I need to sample more often. Well, if I'm sampling my digital values at billions of times per second, I can't get my full 12 bits because I can't crank it through that fast. So I need to come up with new technology that gives me a wider number of bits, more amplification, and can sample, maybe at least an order of magnitude more often. So now I can get lower amplitude that's detectable and higher frequency that's observable. So that's what the acronyms are. It has been postulated, not by me, but by others, that much like we have a microwave cosmic background radio, that we have a cosmic background gravity field left over from the Big Bang and all the collisions that have occurred and all of the vibrations that are occurring even today in big high gravity things, that there are gravity waves that we currently do not have the proven technology to detect, although we think they might occur. And that's another way that you can get the energy out of your quark star as you coalesce, you degenerate your multiple kinds of quarks more into singular kinds of quarks, is, crank out the gravity waves at low amplitude, high frequency, which we can't detect. Does that mean they don't exist? No, it just means we have to create the technology to detect that which is currently undetectable, but which is plausible. So I think you're going to find that ultimately black holes are quark stars, and quark stars, as they're coalescing into a singular type of quark, have a gravity wave hum that is low amplitude, high frequency. So LIGO and Virgo can't detect it because it's like having an AM radio trying to listen to FM. Now, how do we start answering some of this? How about we make some measurements? Let's pick a black hole in the Milky Way galaxy, an older one that's not currently feeding. It's not a quasar, so there's no polar jets, there's no emissions. We might find stars orbiting it, having a nice tight orbit around it, but that area itself is not emitting anything. There's no jets, there's no radio, there's no infrared. It's just a classical proverbial black hole. nothing coming out. We calculate from the orbits of the stars going around it what its gravitational force is. We then map the gravitational force, which is going to be lots of it, into billions of electron volts per speed of light squared, which you can do. And when you do that, you'll come away with a mass number. And if you divide it up, gravitational force by the mass, you'll get a number. If that ballpark number is divisible almost equally, depending upon rounding errors, to a particular type of quark, then I'd say you have your answer of, does a quark star degenerate to a strange quark or to predominantly strange quarks? There's a way of determining it right there. Pick a long-standing black hole, not feeding, no polar jets, not a quasar, no emissions. Determine its gravitational force by the orbits of stars going around it. Mathematically map the gravitational force to a mass. It's going to be millions, trillions of electron volts. Divide that up by each of the different masses of quarks and see if you get a number that pockets to a particular kind of quark or a dominant kind of quark. And if it turns out to be strange, hey, you got it right. I'm an agreeer. I'm a true believer. If you find out it's down quarks, I guess your guess about it being strange was a guess. And you have an observation that says, maybe it's different and science should change based upon observations. But until you make the observations, until you create the technology, it's just an unknown. So if they find out that quark stars are really what we call black holes, there's no singularity required because the amount of packing density between a neutron star and neutrons and down to a singular type of quark is near infinite by comparison. If you think about, I've got a white dwarf and I pack it down and become a neutron star, that's significant. That's like big time. Now, if I pack it down even further and I choose the absolute limit black hole singularity, I've gotten rid of my need to make sense on how tightly I can compact things. But if you bring back in, guys like Pauli and Planck, like maybe you can't take it all the way to a singularity. Maybe there really is a limit. How easy is it to reach the limit? It's damned hard to reach the limit because there's so much space left, even after you get down to quarks. But is there enough left that you can start to, in the absence of gluons, squeeze all the quarks down to one kind of quark? I think so. And I think if you look at the billions of value in quarks, you're going to find that the one with the biggest billions is top, not strange. I think that neutrinos are released as degeneration occurs going from protons to neutrons to quarks. I think that polar jets out of neutron stars and even black holes is because it's just too much. I can't digest it all, and it kind of upchucks. I think that when the degeneration is occurring and there's not so much excess that it creates jets, but it produces radio waves, I think you've got your quasar. But I think that, event horizon in the absence of messengers to produce photons is not so much an event horizon as it is just a threshold in the progression of degeneration. And once you get to this level, I haven't got the particles I need to make the energetic stuff come out. It goes in, it comes out as gravity waves. But it comes out as gravity waves, I call it quark star hum, that we don't have the technology to measure it just yet. But if you want to maximize, if you want to compress it down, think of it as that absolute limit, like a star trying to fuse iron. The absolute limit would be top quarks, and it's the Pauli exclusion principle and the Planck limit that says, this is as tight as it goes, guys. Now, if you want to go beyond there, there may actually be new science. But there's plenty of room left within quarks to get down to singular types of quarks. Plenty of room. Once you get down to that level, maybe Hawking radiation isn't needed, because Hawking radiation is very slow. And if you get on neutron stars, they call them gravity quakes. This is when the crust of the neutron star supposedly rattles a bit because of its spin, and the neutron star kind of stretches out at the equator versus the poles, and you get a slight change in velocity, and therefore crushing of the crust of the neutron star, and it produces huge amounts of radiation. Well, that could be the
Fast burst.
that could be the gravity, not the
Gamma ray fast burst.
Yeah, it's at the bottom right. Gamma ray burst that everybody talks about, but people just theoretically say where they come from. Well, it's neutron star crust earthquakes or quakes. Well, you can have the same thing in a quark star. If I'm migrating from ups and downs to some strange, I may get a quake as I'm pressing things tighter. But even after I get mostly top and I'm converting some strange, I can crush a little more. And every time I crush a little more, I could get a gamma ray burst. Because how else am I going to tell you I've got excess energy to spew? I can do it in gravity waves, but gravity waves may have a threshold. And, gamma is the next thing up. Because, once you get down into what's the highest energy individual photons I can produce, that'd be gamma. Cosmic rays are actually subatomic particles mixed with gamma rays, but gamma is it. So if a black hole is nothing more than a quark star, and if the eventual degradation of a quark star is to a singular type of quark, and that singular type of quark is a top, then a lot of this other stuff, just like, you don't need that anymore. The singularity goes away, the mathematical infinities go away, and it gets a lot more practical. And one of the things that I found during the study was color flavor locking. And color flavor locking says, if I've got a collection of subatomic particles and I go to a tighter cohesion, I may get still a differentiation in my quarks, but now it's not going to go any further because my types of quarks have kind of locked into a steady state, and I get color flavor locking. I've got this many ups and this many downs, and it's good until something comes along and disturbs it. But once it disturbs it and I get to the next level down, I've got another stable state, and that's my next color flavor lock. Well, what's the ultimate color flavor lock? One kind of quark. And if I want to have the greatest possible mass quark, that would be all top. Now, when these final stage energy releases in gravity waves occur, it may not be the quark star itself that is the source of the gamma ray burst. It may be the intense gravity wave passing through nearby neutron stars, which causes their surface to quake in the presence of not momentum changes, but just the gravity change going through that neutron star. And that may be why gamma ray bursts are not predictable, and their energy levels vary. Well, it varies based upon the amount of quark quake they get. And if you've ever seen the evolution of stars, they've got this lovely diagram that starts from here and progresses to there. And I drew one of those things. It's not circular because you don't come back to where you started from, but the line goes left to right over time. Up at the top half, above the line, are the emissions of the stellar objects. Below the line is the phase, the stability points. And then the bottom separated line is kind of like the types. these are my categories. So I've got a midlife star, goes into nova, becomes a neutron star, becomes a quark star. And I don't differentiate a black hole as a special kind of quark star. They're all quark stars. It's kind of like, is a square a rectangle? Yes, it is, because it's a right quadrangle. Well, what if I make all four sides the same length? Now you got a square. But are all rectangles squares? No, but all squares are rectangles. Same sort of thing. Maybe the ultimate quark star is what we think of as a black hole, but there are lesser quark stars that are on their way to becoming one of those, but I still call them quark stars because they're all quarks. So if you look left to right, you've got a regular star during its lifespan, and it's spewing out plasma, photons, electrons, protons, and neutrinos. Stuff. Now, as the star gets towards the end of its life and it's kind of run out of hydrogen and helium, and it starts fusing heavier elements, well, it's still spewing the same stuff. It's just getting more gravity, smaller. Now, once it attempts to fuse iron, it's like, you get lots of stuff out because of the nova. You get heavy elements out, far more than the other particles. You get full atoms out. Once it's quieted down and collapses further, what do you get? Well, you get a neutron star. Well, on the way to that collapse, you get some X-ray and some gamma ray emissions. But you also get electrons, magnetic fields, folks, and it becomes a pulsar. What is a pulsar? Well, that's a neutron star that's got so much coming out that it creates jets, relatively jets coming out the north and south pole. And when that's spinning towards us, we get pulse, pulse, pulse. But if it's tilted towards us and it's all coming out continuously, you got yourself a quasar. Well, they could be spewing gravity waves, and those gravity waves we can detect. So when neutron stars collide into one another, we can see those gravity waves because we got the right technology. But let's say you have something that's even bigger, denser, and it wants to collapse. Well, what's the next step after neutrons? Quarks. Well, on its way to collapsing down into a quark star, it's going to be spewing some more X-rays, some more gamma. For a while, it's going to be a quasar until it switches off. And you're going to get neutrinos because some of that matter that's on the outside of the quark star is experiencing such energetic forces. You get fusion. So you're going to get neutrinos out of it. And you're going to start to get some of that gravity wave that we can't currently detect. As it becomes closer to being heterogenous, moving towards singular type of quark, you're going to start to see your relativistic jets die down. But if some new matter falls in, like it's feeding again, okay, your jets are going to come out, going to become a quasar again, you're going to get neutrinos, you're going to maximize the amount of those undetectable gravity waves until it feeds or it falls below the threshold and it can now consume and degenerate everything that it's got. But once there's nothing more falling in, once you've got a singular type of quark, not feeding, singular type of quark, you've got no normal messenger particles to send stuff out. If you have any erratic behavior like a crust shift at the quark layer, how do you get the energy out? Well, occasionally you're going to have some of those gravity waves you can't detect because of packing changes. You weren't quite there, but now you're there, or you're a little closer to there. So you have a large amount of energy to send out, none of the normal messenger particles. So gravity waves that we cannot with our technology currently detect. So you've got a progression chart. And black hole fits in that entire pattern of quark star with all that we know about black holes. And you don't need singularities or infinite math. It's just there. Now, what happens after that rightmost dot? I don't know. We don't have any current postulations for that. But If you get a big enough one, maybe you get a new universe. I don't know. That's beyond my level of postulation. But if you think I'm the only one going, what's a quark star? Is anybody studying quark stars? Well, I found from 2007 an actual research paper on the Harvard website that's entitled, Do Black Holes End Up as Quark Stars? Now, they kind of took it the other way around and said, well, we don't think of quark stars as being a midpoint between neutron stars and black holes. We think of quark stars as being the next point further collapsed from black holes. So that's what we thought in 2007. And then by 2009, it kind of flipped the other way. Can stellar mass black holes be quark stars? But only stellar mass black holes, not the big ones. By 2017, it went from quark stars being a separate topic to quark stars and what kind of quark stars just being tucked into a discussion of black holes in space-time. And then in 2018, I actually found a paper that says, are black holes actually quark stars? That's the name of the paper. And it gets into Pauli exclusion principle. Basically, you can't crush it down to the point where you have two quarks occupying the same space, but there's plenty of room to get two quarks in the absence of gluons to be really close to one another. Now, when you talk about black holes, you'll hear things like the Schwarzschild radius, meaning how small can a black hole be before the radius of curvature of the black hole as a ball gets to be infinite. You know, the curve of the outside just smaller, poof, infinite. And there is a limit. And once you get to a Schwarzschild radius, you're not supposed to have black holes any tighter than that. But we have observations that say they do get tighter than the normal radius we think of. So must be a black hole. It just went to infinity. So we went from a known value for the Schwarzschild limit to infinite. And astrophysicists come up with infinite as we don't know. Mathematicians don't like infinite because I know you don't know. So infinite is bad news for astrophysicists and mathematicians. It says what they don't know. So maybe it is that if you just take the quarks into better account and you start getting the quarks down to a single kind of quark in the absence of gluons, maybe you got something there. So if you've read the other research, read that one, because that one does get down to, well, maybe the infinite isn't needed, so it doesn't hurt the brains of physicists or mathematicians. And maybe all you have is just a lot more space to compress things down if you started thinking about it as, with the gluons gone, you can have a singular type of quark, and you go to the biggest possible quark you can be, which is top. And then the Quark Stars PBS space-time video on YouTube, they postulate that you get strange. Up and down, you get 50% of it converted into strange, and that's kind of where you stop. And that's a midpoint on the progression to a black hole. But if up and down were to generate to strange, you're on that midpoint along the progression towards maximization, then why stop at strange? I'm okay with it being a temporary plateau, a stabilization point, but why would you stop there when you can have even more energy collapsing down, even greater gravity collapsing down further? There's plenty of space left, folks. So the ultimate limit, I think, is going to be the Pauli exclusion principle. You can't have two particles in the same place. And Planck length limit, we got nothing smaller. So it's kind of like hitting iron. Once you hit those two, You got to come up with something else. But until you hit those two, you got plenty of headroom there. So, and my second postulation of distinction here is, I think absent your messenger particles like electrons, you're going to start sending out your breadcrumbs of energy as gravity waves, and not just the stuff we can receive today, the stuff we don't have the technology to yet receive. So gravity waves become your messengers in the absence of all the leptons being gone.
Yeah, but electrons are not the messengers. It's photons that are the messengers. The the electromagnetic force carrier is photon, not electron. So if you have black body radiation, you can still have photons, even without electrons.
So you're still sticking on the only thing that's keeping the photons from coming out is gravity.
If it's massive enough that the escape velocity is above the speed of light, the photons cannot come out.
Uh-huh. And how do you get to that level?
When you
You
get
have
a
to-
massive enough or a dense enough object in space-time,
And does
then the
that
curvature of the Schwarzschild field it's going to be, circular. It gets stuck in there. It never comes out.
yes, but is the speed of light limit greater than or less than the Schwarzschild radius?
That's
In other
if
words,
it's
the
massive
Schwarzschild
enough,
limit,
if it's
not
massive
infinite, not
enough,
infinite, not infinite, the limit.
if it's massive enough that the escape velocity is above the speed limit, the photons will not come out.
Okay, that's not the question I asked. There is a Schwarzschild limit,
Yeah, that's where that happens.
but what happens beyond that?
Nobody knows.
Okay. What happens immediately prior to that?
Immediate prior to that, you can still see those photons, but they become stuck in the circle because they are close to the speed of light. So for the observer that is far away from a heavy object, black hole or not,
Mhm.
that it is the space-time there is so stretched out that whatever is there from the observer that's looking far away, that stuff never moves. That's frozen in time because space-time is so stretched out.
I wasn't discussing the time aspect of it. I was discussing the whether
Photons, the actions of photons, they are stuck in there.
I was discussing whether it was gravity that was holding in the photons or they had nothing left to generate the photons.
It's gravity that's holding photons.
And that's current theory
Yeah,
because we don't know what happens inside that limit.
we do know what happens until the Schwarzschild field.
But we don't know what happens after that.
No.
Correct. There's a lot of postulation. Some people like to call those theories. They're just computer
Hypothesis.
They're hypotheses. They're postulations. They take principles that they know and they come up with, and here's why, based upon what they know.
Yeah.
But
It's like it's because when you stretch space-time so much, basically you're stopping time, you're changing the properties of space, the local space there, that most of the laws and hypotheses and theories that we work on Earth or near to stars, they break apart. The numbers don't add up. So it is
Mhm.
very hard to actually predict what happens after the event horizon.
So which would have greater gravity, a neutron star or a quark star made of a singular type of quarks?
Quark star,
Of course.
it doesn't matter which kind of quark they're made of. If it's a quark star compared to a neutron star, of course it's going to be a denser object
Right.
and the escape velocity would be higher.
Right. And regardless of the diameter, at what mass would photons no longer escape? Is it two
When
types
you
of
get to
quarks? Is it
mass where the space, the escape velocity of photons gets to the point where they cannot escape because uh, the escape velocity is higher. And the other thing that it is like one of the things that people tend to forget about when you stretch space-time, when you do that, you make the photon, in the case of what we are talking about, to move towards to from visible to red to radio to the point that they get so stretched that they become invisible. So as like space-time near to the event horizon are extremely stretched, so everything just goes towards to the red and radio and then become invisible because they get to a point that the wavelength of the photon gets stretched to infinity.
well, it doesn't have to get stretched to infinity. Infinity is
From our point of view, actually.
actually
Because
it's far less than that. Infinity is just it's a convenient end stop in math and
close to
physics. But
10 to.
yeah, but even after it becomes radio waves, microwaves we can receive across the universe. AM we can't. AM gets stopped by a lot of things along the way. So once it stretches from infrared into microwave, we can still see that. If it stretches any further down to even lower frequencies, it's not that we can't receive lower frequencies, because we absolutely can, and we do it all the time in radio receivers here on the surface of the Earth. The problem is there's so much stuff in between there and here that we can't receive it because it doesn't make it. It doesn't get from there to here. It's not that it stretched out to infinity. It's if we put a radio telescope on the far side of the moon and we make it big enough in diameter, we can receive longer wavelengths than microwave. And if we can receive longer wavelengths than microwave, we might actually receive from black holes radio waves that we cannot receive today, because we stop at microwave because nothing gets any further. So there's always headroom. There's another threshold out there. We're just at a plateau of our technology, our observation site, and what we've seen so far. Don't stop there.
But the event horizon math and the event horizon observations are well established and confirmed that everything that happens prior to the event horizon we do understand quite well.
Do we receive lower frequencies than microwave from energetic objects in space?
Yeah, we receive radio that's way much less energetic than microwave.
Okay. And how far can we take that without getting to infinity?
In the case of our technology, we need antennas that will be larger than the planet to receive even lower frequencies. So that's our technological limit to receive, but they tend to go that way.
And so how big does the antenna on your mobile phone need to be?
For what?
Is it a full wavelength? Is it a half wavelength? Remember when mobile phones first came out and they had like a 3/4 of a foot long antenna on them, because they were a good portion of the wavelength of the microwave range that the radio was operating in. Well, how big is the antenna on the outside of your mobile phone today? It isn't.
Zero.
It's essentially
a fractal antenna
smaller than a postage stamp. So if we already know we can receive longer wavelengths using tiny antennas because they're fractal antennas and because we have high amplitude, low noise amplifiers behind it, there's no reason why we need an antenna bigger than the planet Earth to receive longer wavelengths. We just need
Yeah, but
fractal antennas.
if you have a wavelength, I'm exaggerating here.
No,
But
no,
if you have a
I'm
wavelength of
proving
the
the point.
size of a galaxy, we cannot capture that one.
And I just stated something that disproves your point. If the radio frequency wavelength of your mobile phone is many times larger than the fractal antenna inside your phone, and yet your radio in your phone works just fine, transmitting and receiving with this little tiny antenna that's much smaller than the wavelength of the radio, why can't we do the same thing with other wavelengths?
We do. We are doing actually a lot of those things. We can capture nowadays wavelengths that we couldn't even a decade
Exactly.
ago.
So the whole precept of we're going to need an antenna the size of the Earth or bigger than the Earth, like that just doesn't carry with reality of mobile phones. Because the antenna in a mobile phone is much smaller than even a fraction of the wavelength of the radio frequency that the phone is using.
Yeah, but anyway, photons, they're generated inside of a massive object like a black hole, would have a circular path that points them back to the black hole. And even the ones that could escape, that are actually at the edge of the event horizon, from the observer that is just outside of the event horizon, that wavelength is so stretched out that they tend to go to the direction of the invisibility.
Invisibility is just your word for can't receive?
No, that is stretched out to that they cannot come out of the black hole. The photon doesn't come out.
So do all plasma discharges from a star leave the star?
No, normally
No.
it is the stuff that is,
Normally they come out a ways and fall back.
no, some of them are the disk around that has friction, and that friction and the magnetic fields end up being the discharge. Sometimes not really the stuff that is on the surface of the star, but just outside on the disk.
Yeah, the plasma travels along the electromagnetic field coming out of the surface.
Yeah.
That's how it's curved. Well, if there are still electrons on the surface of black holes, then the light coming out of it would travel
It's on the disk. It's from the
travel
disk.
along that back to the black hole.
It's from the disk. The light that we see outside of the black hole is from the disk, not from the black hole.
Right, because it's impossible. And the reason why it's impossible is that's our current explanation.
Yeah.
And we have computer simulations that prove that. But we have only looked at the material falling from disintegrating stars into black holes and not being able to detect them after a while. And that's our basis for why black holes are doing that, based upon gravity rather than something else.
Yeah.
Yeah. So, and galaxies were one-time nebulas. So we're at a plateau in more ways than one, because it's 11 minutes after midnight.
Yeah.
So, as I said, if you follow through on the postulation, I don't even think Hawking radiation is needed. But do the research, get the funding for the technology, time will tell. And I have a long list of research material.
But that was cool. That's really, really
Well,
head scratching.
yes, the PBS video you gave me on strange stars was more than enough for me to dig deeper on the research. And that's where I found that final research paper from 2018 that basically said, are black holes nothing more than quark stars?
Enjoying, I own you to find. I was looking for a picture on my computer. It was probably in the other computer that shows the inside of atom, or the atom, no, the neutron, the proton, and it is like the best analogy ever. So they have three ducklings of three different colors to signifying the chromodynamics, and then they have three little glues, and the ducklings are pointing up or pointing down to signify the spin of the duck. So it's like the cutest way to show what is inside of a nucleon. So they have like three little ducks inside of a ball, but I couldn't find that picture. It's probably on my other computer. So I'm gonna look for it, and next week I will try to find that. But it's the best analogy ever and the easiest way for you to visualize what is a nucleon.
I gather everybody would like to see it. Sounds like fun. Very nice.
No, it was Moreau. I made the picture because I stole it from Crash Course, one of the videos of Crash Course, so I couldn't find the ducklings.
Now, what I wanted to show was when we start talking about electrons and neutrinos and stuff, how does that fit in all the other stuff that goes on? There are things called fermions, hadrons, and bosons. And if you remember in the table, you saw like Higgs and gluons and W's and Z's and stuff like that, and photons. Those are over here in this bosons category. But over here on the right side, you see that's where the electrons and the neutrinos are. Those are fermions. And then you see kind of the crossover, the like Venn diagram overlap of things like neutrinos and protons. And earlier, Helen was mentioning kaons and pions. Those are associated with the mesons.
Oh, I forgot about the pions. I could
Yeah,
only remember kaons, and
Right.
I thought was spelled kaons, but it's kaons. Oh my
Yeah,
goodness,
yeah.
I'm losing my mind.
So
I'm forgetting the particles.
as they started out with atoms, and we started to break them apart and get electrons, protons, and neutrons. Okay, we got a plateau. It's good. It's all working. And then you build the next more energetic collider. You start to get like there's more breadcrumbs coming out. What do we call those?
Well, to begin with, the word atom means indivisible, non-divisible. It's like no.
Yeah.
And tomo is division or part. Like when you go and buy like the old encyclopedias, every book is a tomo. It's a division of the encyclopedia. So atomo it means non-divisible. So that's the would be. And yeah, just to begin with, the where we start is the stuff that start to divide.
Yes. And right now,
But it's 3,000 years of technology, not shabby at all, to understand that things are made
no,
of
it isn't.
small
No, it isn't.
particles.
And I will not discount it any amount except for the fact that, well, those guys way in the past had it wrong, and we've got it so much betterer now. Well, just go back one step and say, how about that Newtonian to
Oh,
Einstein?
Monroe, can you look at the picture that I sent on the last chat post? That one is a good one. Okay, now yeah.
Yep.
So you see a proton down is the gray, and an electron is the little tiny red on the left.
Right.
The one on the bottom.
Yep.
That's the proton.
Uh-huh.
And then Monroe's point out that the most massive is a top
Yep. By a lot.
by freaking a lot.
Yes.
And the one that makes a proton or a neutron is the up and down. So you see they're kind of a tiny, and for them to make something like a proton or a neutron that makes an object that's way much more massive, because most of the mass of the baryonic particles like neutrons and protons and stuff that make stuff that we can touch, the gravity and the mass is made more because of the connections of the gluons that keep stuff together, and the electromagnetic forces and the strong forces, the weak force. Of course, that we found part of the missing interaction that was predicted finding by the Higgs boson, but this is only a fraction of the mass. Most of the mass is between the strong and weak forces inside the atoms carried by the gluons and in the chromodynamics of the up and down
And-
quarks.
And the progression is pretty obvious here when you say, okay, I'm going to take a neutron, which is 2 up and 1 down, and I'm going to take a proton, which is 2 up and 1 down, and I'm going to degenerate that to something with greater mass that is now 1 up and 2 down. But that's not a huge difference. But then you say, well, I'm going to take 50% of that ups and downs and make them into strange, which is bigger, okay? But I'm still going to have some ups or some downs left over. Well, if the process is towards bigger, heavier, greater mass, that's a stepping stone along the way to go from.
But
ups
the
and downs to
process
strange.
not to bigger and heavier mass, the process to go denser and denser.
Right.
The idea is to make the object even denser
Yep.
to cause the space-time to bend more and more.
Exactly. So if I wanted to maximize that, I would make everything ups, because that's the smallest grain of sand I can pack in a fixed size of space. And absent gluons, there's nothing pushing them apart anymore. I have stability. So why wouldn't I collapse everything down into ups?
Then the chromodynamics wouldn't allow it.
Exactly. The pretty picture in the math wouldn't work.
Yeah.
Right.
But this is a good showing of the volumes
Oh, yeah.
and
So,
mass.
so how many ups and downs can I fit in one top? Many,
It's
many
like
thousands.
you have,
many
Monroe,
thousands.
you will not change the size of the quantity of quarks, but you can change the flavor of the quarks.
In the absence of gluons, why can't I change the number of quarks?
No, won't change.
No, I said, why can't I? What is stopping me from changing it?
How you would do that?
No, I think, isn't it a fundamental quantum number like the baryon number and stuff? I think it's just a fundamental number that they just made up when they made up quantum chromodynamics.
Exactly.
The math worked out.
Exactly. It's charge. You add the charges together for the end particle you seek. You add these two together, you add these two together, you get a proton. You add these two together, you get a neutron. You don't have protons and neutrons.
But there are several different numbers. It's not just the charge. It's like the quantity.
Yeah, you need to obey the numbers too. So they still have to have two kinds of the ones that the same line. So you would have 2/3 and minus 1/3, always the same quantity. They could change. It's like they are interchangeable. Like the top, the up, and charm are the ones that have the same okay, so that if they get changed the flavors of fermions, okay, an up could become a charm or a top, a down could become a strange or a bottom. That Adam is correct.
And they're only doing that based upon charge, not mass.
They have to keep the same equilibrium.
A proton and a neutron have two different equilibriums.
Yeah, but when you smush together, you become making a neutron. You get an electron and a neutron and you make a neutron, electron
And
and proton.
once you smoosh the neutron together and there is no more neutron or proton, and all you have is quarks, why does it
They
need to
keep
come
the
out?
same general level of charge.
Why? There's no higher order particle that it has to add up to equal.
So you can change the flavors, but you have to keep the charge. Adam is totally correct.
So I've never found a charm by itself. I've never found a strange by itself. I've never
No,
found a top by
not
itself.
not even an up or down in the case of the science that we can do on planet Earth. But with the energies and pressures and gravitational pull on those very massive objects, that's the idea that that might be happening.
I absolutely agree that in order to have protons and neutrons, you have a specific pairing of ups and downs and gluons holding it together. But once you get below protons and neutrons, there is nothing constraining you anymore from how many of what kinds of quarks you have. There's no higher order particle you have to balance out.
Yeah, but where would they come from?
They would come from the original baryonic matter.
Yeah, but the baryonic matter can transform to things that they can transform. They like there are things that can be transformed in other things, but they follow rules, and those rules, that's the way it is. Like,
Those rules are only for the creation of higher order material. So they follow rules because you want a neutron, because you want a proton. Well,
yeah,
protons and neutrons don't exist if you have a quark star.
sure.
So why are they still following rules that are obsolete?
But in that kind of masses, some of the rules that we follow is still work. The math still works.
Well, Monroe, of course, we say there are no protons or neutrons. Those are baryons. There's a conservation of baryon number, and I agree with you that if there are no more baryons, there isn't going to be a conservation of baryon number.
Right.
The question is there a conservation of either quark number or even more, a conservation of quark number of particular types? We know that the flavor can change because the weak force does that, but I don't know. That's a good question. It seems to me, you would just seem there will be this conservation.
It's based above my
know.
pay grade.
Yeah.
Yeah, I'm trying to research it now.
Okay.
Well, read the paper that I included in the presentation of our black holes, quark stars. And what you'll find out is they go through the math of quark. And once you find out, oh, I've got a new stability point here, once I take the gluons away, and once I no longer need to make protons and neutrons. Now I can have, like, if I take my ups and my downs and I convert 50% of them to strange, it can only be the downs that get converted to strange, because the downs are minus 1/3 and the stranges are minus 1/3. But I get to a higher mass. So I'm going from 1 up and 2 down to 1 up and 2 strange. And I can now go from 4.7 million to 96 million. But if I want even more, I'm going to have to squish the 2 downs into 1 strange. So I'm going from 2 times 4.7 to 1 times 96. And I keep the same charge and I keep the same spin. That's stability. So if the math is supposed to work, then the math should always work, not just when it's convenient.
Well, and when in black holes, the math breaks apart.
Maybe it's the math. Maybe it's that the math doesn't break apart. It's more that it doesn't work the way we think it works. It works the way it does work. And when you start saying, well, the only way I can get this to work is if I have a singularity and an infinity. The astrophysicists will say, singularity, you lost me because you just don't know, so you're just coming to an absolute. The mathematicians will look at your formula and go, well, when you figure out what that infinity actually is, let me know. There's more out there. This is just a stability point.
Yes, thank you very much.
Okay.
Bye-bye.
Okay, and now I will stand down from my soapbox and ask if anybody else has any other comments or questions. Things progress. When do you stop? You can feel free to stop at plateaus and take a break, but keep with the progression. All those are plateaus, and plateaus are not where you stop. So progressions. Not, the next step after finding dots and connecting them is if there's at least 3 dots, they're going to be on a line or a curve. So not only find the dots, not only connect them, follow the curve. Okay. So
I'm still trying to find the picture that I saw. Because there will be.
I've seen the video. It's a video. I think it's a Veritasium video, actually.
No, I think it's Crash Course.
I think I remember, because I didn't watch Crash Course, but I think I remember seeing a quantum chromodynamics ducks picture on a Veritasium video.
Mm.
And I agree, the ducks are a good analogy.
It is the best one. I actually printed out. I don't know if I'm gonna be able to.
The only
find it.
only part that doesn't work right about it is he has binary color schemes. So
Give me a second.
if I've got 6 kinds of quarks and I want to mix them, I can't come up with R, G, B, and white. I've got to have a couple of other colors.
I don't know if you're guys are gonna be able to see it. I'm gonna try to show.
I've seen that
duck
before.
wheel.
You used to use that in class. Oh, let me make you
Comes and goes.
let me make you the spotlight.
Okay.
There you go. Now do it.
Let's see if I can do that. Okay. So this would be
Nope.
in my face. My eyes need to.
Hold both hands in front of it.
No.
No, it's looking for eyes.
Yes, I know.
Okay.
Okay.
Nope. Okay, there it is. Okay, you can see the red, green, and blue ducks.
Mm-hmm.
Okay.
And little glue.
Yep. And then you
And
have
then
the gluons,
this
which is
way-
the little glue.
This way you have a neutron. And then if you do this way, you have a proton.
Right, but that's singular. You've actually
So
got
this is
2
like
of
the
one,
best
2
analogy
of one,
to
and 1 of the other.
understand that what are quarks.
Yeah.
So I had a problem that I kept forgetting the word quarks. When I finally saw this picture, I never forgot what are quarks, because when you're learning a little bit of quantum physics, you have kaons, prions, and then you have all the ons, like baryons and
Fermions, leptons,
it's
gluons.
the name of it. What is the name of it? Stuff that I cannot forget. And then when someone did this, I'm like, I will never forget. This is
Right.
perfect quark.
And
So
glue for
that's how
gluons.
it works.
And glue for gluons.
The little glue bottles
Yep.
for gluons and the quarks.
Yep.
Changing color.
But like I said, that works great until you ignore the fact that you need 2 of them.
Yeah, of course.
I need
you
1
know.
up and 2 down, or 2 up and 1 down.
Oh, I only need this one and 1 hydrogen to make one electron to make hydrogen.
Uh-huh.
And only need 1 of this.
Right. You have a plateau of stability until you say, well, what about the other 114 elements in the periodic table? They're different.
Yeah, and then you stack them a lot.
Then they're different.
Yeah, I found at least, I don't know where's the original picture. I made that one. I stole the idea from one video, or maybe I took the picture and
Yeah.
I printed out and put, in my classroom.
A little bit of Google searching, and I think you should be able to find it.
No, that is no Google search because I stole it from a video.
How do you get to the video?
I'm trying to find the video, but so far nothing. If I find during this week, I will send to you to send for you to send to everybody else.
Well, you can always ask the chatbot AI.
Oh yeah.
Yeah, ask chatbot. You'd have to set up an account, but it's free.
But how am I going with this accent tell the chatbot to find a duck inside of a atom?
Because you type it in text, you don't speak to it.
Okay.
Yeah. And you don't use text. You don't use speech to text on your phone because that's not going to work.
No,
Yeah.
normally doesn't. I'm too busy, and I text Monroe like talking. Like half of the words are shit because with the accent, the thing doesn't understand me.
That's okay. You don't have to go back and correct it. I understand.
Yeah,
I've had over a decade of translation, so I don't have a problem with it.
Yeah, like did this time came out something because I didn't verify. I was already at work. I was making coffee and talking about electrons, protons, and neutrons, and probably people hearing me. What the heck she's talking about?
Well, back to our days at Denny's, we'll have a conversation about quantum chromodynamics, and people are like, "What the hell are they talking about? Colors of paint?" Yeah, it's chrome paint.
But I found it was a super clever analogy to explain 6 dimensions inside of a tiny little thing. For me, the solution of using color, especially that applies to antimatter, it is like so genius, so simple, and so easy to understand. I found it that the person who thought about to use color as the analogy, it is
and it works, and it
born
works.
Teacher.
It works right up until we get the next generation of particle accelerators to break things apart further. And the first thing that will happen is all the existing physics subject matter experts will discount it as it doesn't fit the model. And then as soon as more and more accelerators get that technology and the numbers start to crank up to the sigma 5, sigma 6, it's like, now what have you got to say?
But Monroe, it doesn't take out the cleverness of someone.
No, it doesn't. No, it doesn't.
Physicist.
No, it doesn't.
Who had only math in a head.
Yep.
And had the idea or had enough like education in other areas of art, understood art to think about to apply something that is just numbers and use a clever idea to use color to explain something complex. I found this really clever.
Well, it's kind of like the people that come up with mnemonics for the names of the planets, and then some jerk goes out there and says, Pluto is a dwarf planet, change the last word.
Or
we can't just change the last word because then it doesn't balance out. We'll have to change all the words. And they did. They came up with a new mnemonic. It was a different phrase with different words, and it fit the number of planets to be 8, not 9. So, yeah, they can be clever, and it can work for a long time until additional observations come into existence, and then you can hold it for a little while, but you eventually have to give in.
It doesn't. I'm fan of who thought about to use chromosome, just like the Feynman diagrams. The math for one diagram takes 2 pages of numbers.
Yep.
And he came about of having math to explain how the decay of subatomic particle happen that even a person like me doesn't have enough math can understand. This is like genius.
Well, I think it's because he understood electronics and schematic diagrams and came up with the schematic diagrams for subatomic.
Oh, come on. Feynman named his theory QED,
Yep.
and then formed quantum electrodynamics to
Yeah.
match the Latin words for "thus it is proved." He's just a genius. It's the best
What?
acronym
Can you
ever.
repeat what is it?
QED.
He came
You
up
know
with the
his
acronym beforehand.
The
Because
acronym
remember,
QED,
QED is quite easily done.
it's quod erat demonstratum.
Yeah.
Thus it is proven. It's
Yes.
the formal Latin words that you use on any proof. So for his theory, quantum electrodynamics, he thought, okay, how can I name my theory QED? And came up with quantum electrodynamics
Yeah.
for the same words that end every formal proof. He's just a
Such an ass.
genius. He's just a genius. He doesn't just know a little
Just a
bit about
genius and
electronics.
super funny. I have a
it's-
book of him that I kept reading. Like whenever I travel, I bring that book around. Is Are you kidding, Mr. Feynman? So
Yes.
he's talking about him exploding his garage and doing stuff and just having fun during and then coming back from the university and working in chemical industry but not really caring what he was about. It was like it's some semi-autobiographical but full of like jokes and stuff. It's a really silly book, but he's like a funny genius. Like,
Is
yeah.
that the one where he breaks into the safes at the Manhattan Project?
Yeah,
Or is
I
that a
think
different
so.
one of his books? It's like
Yeah, but it's
something like "Surely You're Joking, Mr.
yeah, surely you're
Feynman."
joking,
Yeah,
Mr. Feynman. Yeah, yeah,
terrific.
that's the one. I carry around like whenever I travel, I bring that book. I'm reading and then going like this in buses or airplane, like.
Yeah.
I wonder if any of his colleagues referred to him as
I think it was Monroe who gave him that book.
yeah. Well, I wonder if any of his colleagues ever referred to him as Smarty Pants.
You know, it's Diane who gave me a raft of information on Feynman. I don't know why I hadn't even heard of him. I don't know how I hadn't heard of him going through college. But Diane, you always see his lectures and stuff on the internet, and he actually says, I don't care about these prizes. The neat thing about science is discovering it. Who cares about the prizes? And he got the Nobel Prize for showing that that an electron. What is it he showed about an electron that's the equivalent of time travel? I don't know. He got a Nobel Prize for that, and he always says, I don't care about those prizes. What do I care about prizes?
I think it was like showing that a positron was electron moving to the past or something like that.
Yeah, that's it. And do you remember in the book he was saying that he went to Brazil and he didn't realize that they spoke Portuguese in Brazil, and he had to learn it quickly. That he thought they spoke Spanish there when he went to work there. Yeah, he's hysterical.
I think it was for proving the relativity theory, observing the solar eclipse in Quixadá, if I'm not mistaken.
Yeah, I think he played the conga drums and hung out at strip clubs and stuff like that with no being ashamed of it or embarrassed or anything like that.
He was a heap. Like he was, he couldn't care less.
Just remember, it's the physicists that have fun and the mathematicians that are boring.
He was like super fun, and like this book is like hilarious. I keep reading the same book and on and on. Yeah. Well, not anymore because now I'm stuck watching Korean soap operas. Correct.
Oh, they're great.
I took a nap before work, after work, so I could be awake for the presentation. Now I'm done.
Well, we're after 1 a.m., so I think our party's done for today.
We will.
Anyway,
it was great, and it was a real brain twister tonight.
Yeah.
Yes.
If you're going to have an organization called Broward Astronomy, you should have some intense astronomy stuff in there. But remember, in the presentation, nowhere is there an integral or a derivative symbol.
Ooh.
There was no math.
Oh.
The only math was 1/3 plus 1/3 is 2/3.
Two-thirds, yeah.
Yeah.
Yeah, exactly.
There was
All right.
basic fractional integer math, and that was it.
Well,
Yeah.
for me, it always ends like infinity.
Get rid of those damned infinities. Infinities
Yeah.
are just a way of
Yeah.
saying, I don't know.
But you
Right.
know, watch the video of Strange Stars. It's really fun and
yeah.
explains neutron star. Actually explains the process
Mhm.
from
Degeneration.
neutron star going down. So this is really good and very informative.
But the only way he describes it gets to strange stars is that one we know lasts longer than other types of higher mass quarks.
And by the way, there are so far 3 candidates, so it's pretty awesome.
For quark stars, yes.
Yeah.
I think if you ask me, I'd say every black hole is a quark star, just at different points along the degeneration. And then you don't need all those thinking infinities and quantum singularities and Hawking radiation and all that stuff. Anyway,
Oh, that silly stuff that gives Nobel Prizes. Nah.
well, remember before the Nobel Prizes were given out, it was silly stuff.
Yes.
Yes.
The Ig Nobel.
Or did you think
Nobel.
that? Or did you think that optical tweezers were something that physicists didn't laugh at?
Most likely.
Very likely. It took how many years after he did the research and proved it before he actually got the Nobel?
Yeah,
8 years?
right.
Come on. Sometimes eventually people just say, I think you're barking up the wrong tree or you're backing the wrong horse. And you go find other ways of doing it.
People,
So-
I cannot stay awake anymore. I'm done.
Yeah.
I'm gonna
Good
go,
night.
okay? Bye-bye.
Good
Have a
night.
good night.
Me too.
We're just talking
Good night.
minutia, so okay.
I'm just trying to figure out how to leave. I don't remember anymore.
Just say goodbye.
No, to push the correct button.
Well, I'm going to push the correct button and stop recording.